Welcome back to our unit on the unit circle. We have now gotten well in hand, or at least we're starting to wrap up anyway, as we will in the next class, everything there is to say about trigonometric functions and their graphs. So we know where they're defined, we know how to evaluate them, and now we know how to graph them. So the time has come for us to try and undo them. That brings us to inverse trigonometry. You see, so far in this course, we have looked at things like sine t or cosine t and asked, okay, so when I go t equals some number, so when t is, say, negative 4 pi over 3, what is sine and what is cosine for that number? And so, in that case, respectively, right, sine of negative 4 pi over 3, that means I rotate clockwise 4 pi over 3 on the unit circle, I end up in the second quadrant. The sine value is positive, cosine is negative. Sine specifically is root 3 over 2, and cosine is negative a half. And that's generally what we've done so far. We've moved on the unit circle, we got to some point, we knew where we ended up, and we used those coordinates to find sine, cosine, tangent, etc. Well, now I want us to do it the other way. Suppose instead we knew where we ended up, and we needed to figure out what we did to get there in the first place. For instance, suppose I knew that sine was negative a half, and also that cosine was root 3 over 2. Where am I? Or what is the value of t that produces those two outputs for sine and cosine? So for this example, we could just plot that point, right, cosine comma sine on the unit circle, right, cosine being x and sine being y. That means that I would be on positive root 3 over 2. Yeah, positive root 3 over 2 for x and negative 1/2 for y. So that would put me about here-ish. But that's not always going to be the case, right? I might not just necessarily know when sine is some number and when cosine is some number. Maybe I know, for instance, tangent. Maybe I know the ratio of coordinates. Or maybe, as we'll get later on in the course, I have some series of trigonometric equations that are not just necessarily in sine or in cosine, but in sine squared or cosine squared, or sine of 2t is some number, and we have to backtrace off of that. So it is going to be important to be able to know where I am now and figure out what I did to get there. So for this example in particular, we're starting off small. I know what sine is, I know what cosine is. I'm going to ask two simple questions, and then we're going to get to the bottom of it from there. For instance, what values of t would make sine t equal negative a half? There's two separate places on the unit circle where that's going to happen. Also, there's two separate places where cosine is root 3 over 2. So it might be possible that this is an impossible construction. It might be possible that all the values of t that produce this are at the same time none of the values that produce this. Or maybe there's some overlap, maybe there's just one solution. Let's look and see. So on the unit circle, sine t is negative a half in two different places. One is here, and the other is over here. Right? The y value on the unit circle happens at two places to be negative a half. So it happens at 7 pi over 6 and 11 pi over 6. And of course, all coterminal points as well. Also, cosine is root 3 over 2 in two places. When pi over 6 is my value, or when negative pi over 6 is my value, or 11 pi over 6. So, to satisfy both conditions, there's only one place where that happens, and that's when t is equal to 11 pi over 6 or coterminal. Therefore, the solutions to both of these, this and this, is 11 pi over 6. I want us to recognize something straightforward here. Actually, it's not that straightforward. That's why I prepared this graph. So forget what I just said there. What I want us to recognize is as we rotate around the unit circle, as we're moving around, or even more generally, simply as we're rotating, period, because we'll get into angle measure very, very soon, I want you to recognize that no matter where we are, no matter what my x and y coordinates are, there's always two separate points that have the same x value. So they have the same cosine. Specifically, if t works, then negative t works. Also, as I'm rotating around, there's always another separate point that has the same sign value. And that is recognized to be not negative t, but rather pi minus t. Or negative t plus pi if you must. So we have two separate values for sine that always give the same number out. Also, just because it's going to work out this way, tangent as well, right? Tangent is periodic with period pi instead of period 2 pi. And so if one number works on the unit circle, you go pi around, you're going to have the same tangent as well. What I want you to realize from that, that's not the right thing. What I want you to realize from that is there's always two distinct points on the circle having the same value for sine, two different distinct points having the same value for cosine, two distinct points having the same value for tangent. Right? Sine of pi minus t is always equal to sine of t. Cosine of negative t is equal to cosine of t. That's the even property of cosine as well. And also, tangent of t is equal to tangent t plus pi. So this brings us to an unfortunate fact. The simple, sad fact that the trigonometric functions, such as we have them now, are not invertible. And that shouldn't really come as too much of a surprise to anyone, especially if you have had any exposure to the horizontal line test in your pre-calculus algebra class. Right? We recognize that sine of x, which does not pass the horizontal line test, will not have an inverse function. So we can't just directly undo sine to get at what's inside. Right? Returning back to this problem statement, there is no operation I can do to undo sine of t to get just at t. There is no value, there's no function, there's no operation to do that. Similarly, I don't have any inverse function that will guarantee the right value for t to guarantee cosine t of equal to root 3 over 2. Right? That's because we get two values. It happens at two places. And functions need to always have one output. So I might be able to create a function that gives me one of these two numbers, or one of the two numbers that would have created cosine of t equaling root 3 over 2, but never both. Functions can only give me one. That said, though, doing just that much, getting just one, maybe not the right one, and certainly not all of them, just getting one is still going to be very useful. And so we are going to, not necessarily for all of sine or for all of cosine such as we have it defined, but maybe just for a piece of sine or for a piece of cosine, be able to make an inverse function for those. And so I just want you for right now to recognize that there is this ambiguity that arises whenever I'm asking questions like, what is the value that gives me sine of that value equaling a half? There's two places that happens. And same for tangent, same for cosine. It's always going to be the case that there's two distinct points giving the same output for each of those functions. And while that is the case, we're still going to want to make an inverse function that gives us just one of those. And then, as we'll see going forward, we'll be able to account ourselves for the other one. So hopefully this video has shown you a problem, maybe not one that you've yet considered, maybe one that you have. And in the next few videos, we will start getting to the answer, getting to our inverse function. Not truly an inverse to the functions as we have it defined now, but as to a piece of them. So, if nothing else, hopefully that's piqued your curiosity for what's coming down the pipe, and I will see you when we get to that. For now, though, let me know if there's any questions about this ambiguity that arises on the unit circle. And also, if you still have any lingering concerns about graphing trigonometric functions, let me know about that as well. In our next class, we will get mostly that resolved, and also we'll start to look a little bit into this ambiguous case. Ambiguous case. There we go. So I hope you have a good weekend. I hope you have a good day, and I will see you at our next class.